Okay, so our next speaker of this causality session this morning is Jan Ambjørn from the Niels Bohr Institute in Copenhagen, but luckily we can also call him a local here. So Jan is known for his many works in quantum field theory and quantum gravity, but perhaps most for being an initiator of the dynamical triangulation approach, starting in string theory, but later also in the gravitational path integral. Causality entered the business with the introduction of CDT together with Renate, and I'm happy that he agreed to give this focus talk with an update on the CDT approach to quantum gravity. Jan, please take the floor.
I'd like to thank the organizers for giving me the opportunity to present this work. Okay. So what I will discuss today is the search for an ultraviolet fixed point using the lattice theory called dynamical triangulations. Well, the main goal for quantum gravity, at least in my formative years in the 70s and 80s, that was to obtain a background geometry, preferably the one we observe, and to be able to study the fluctuations around this background geometry. And what the four-dimensional CDT offers to us is a non-perturbative quantum field theory definition of quantum gravity, or I should say some kind of quantum geometry. It's our task to prove that it eventually can be viewed as quantum gravity. It's a background independent formulation, and what it also offers to us, as I will explain here, is an emergent background geometry and the possibility to study the quantum fluctuations around this emergent background geometry. So pretty good from this point of view. But of course there are problems for any theory of quantum gravity and also for a lattice theory of quantum gravity. So I listed some of them here. Well, first of all, one should actually define this theory, and what we want to do, we want to have a real mathematical definition where one might, like in the path integral in lattice quantum field theory, where you have a functional integral which is well defined, but of course it's your task to prove that you can take some kind of continuum limit of that. And we have to face the non-renormalizability of quantum gravity, and we have to provide evidence, as I said, of a continuum limit, and that this continuum limit has the desired properties of whatever theory we think about. And well, we also have to face the possibility that there might not exist a continuum quantum field theory of gravity definable at all scales. Of course, there exists an effective quantum field theory, but it might not exist at all scales. So if that is the case, can a lattice theory be of any use? I will not have real time to discuss point 4, which is quite interesting, I think. So I will just answer this in one word: yes. And I will mainly discuss point 1, 2, and 3. So how to define the quantum theory? Well, we have the classical action of gravity, and we can define the path integral via the quantum theory via the path integral. And the path integral is wonderful. I mean, this formula is, oops. So yeah, it is a wonderful formula. Any classical action, you put it in here, and here's my quantum theory. But of course, the problem is the devil is in the detail, of course, of defining this. And in this case, what is the precise meaning of this integral here over geometries, as I've written it here? So classical gravity refers to a manifold with a metric and Lorentzian signature. If you get this perverse idea to rotate to Euclidean signature, then anyway it refers to smooth Riemannian manifolds. But we know even in quantum mechanics, I mean, the path integral is not over smooth paths. I mean, we have to integrate over all kind of fractal paths, and they are continuous. So it seems that as a minimum, we would have in any path integral to integrate over continuous geometries. and this is a very unwildly concept actually. Also, what should we actually include in the integration, or should we integrate over different manifolds? Well, in string theory, we are clearly forced to integrate over different manifolds because this string can split up and join and change topology and so on. But in quantum gravity, as such, it is less clear. And CDT, which I'll talk about here, it takes a minimalistic view on these problems. One fixes the manifold, I will only here discuss the situation where the manifold is R, which is the direction of time, and S3, which is a compact space. We will actually use, to define the partition interval, we will use a subset of continuous geometries. In fact, a subset of what is called piecewise linear geometries that can just be constructed by gluing together identical building blocks for synthesis. So the hope is that these are dense in a set of continuous geometries. And well, this has basically been proven in 2D that this is true. If you have the right measure, I mean, of course, this measure has to be quite coarse. Some Gromov-Hausdorff measure of some fancy mathematical measure of this, but it is that's basically the hope. So inspired by canonical quantization, we will assume a Lorentzian signature from the outset, a hyperbolic space-time, and a time foliation. And then we triangulate this using the building blocks. And then for the action, we should use some action there, and we put in the Radji action for piecewise linear manifolds, because this is a very nice action in the sense that it doesn't need coordinates. Once you know the lengths of the links in the triangulation, which is a kind of diffeomorphism invariant concept, then you know the geometry. You can reconstruct the geometry. What is a somewhat kind of remarkable aspect is that if we build up now these CDT triangulations, and I've tried to illustrate them here. You have the time slices here. I'm reading R3, it should really be S3, but this is an old figure, so I didn't change it, okay. So we have triangulated the spatial slices here with tetrahedra glued together in all possible ways, compatible with the topology of S3. And then we connect them, the slab in between, we fill it out with force synthesis in some specific way. The one tetrahedra here is connected to a point here, a triangle here is connected to a link here, such that we get force synthesis in between. And then we glue these together such that in the slab in between, the topology is the same as the spatial topology. And we sum over all of these, and what we use is this Radji action in the partition. But the remarkable fact is that we can now rotate, for each of these kind of Lorentzian geometries, we can actually kind of rotate them to an Euclidean geometry, where each building block now is a four simplex, where all links have the same length A. And this length is then going to play the role of we imagine, as a diffeomorphism invariant ultraviolet cutoff of our theory. Exactly like the lattice length of a link plays this role in ordinary lattice theories. And another remarkable feature is that if we take this Radji action, which in general is very complicated if you have some kind of triangulation, if you use identical building blocks, then it is simplifying in a dramatic way. So now let me have a four-dimensional triangulation T, and let the number of building blocks be N4, and the number of triangles in this triangulation be N2, and the number of vertices be N0. And then the action is just this expression here, K2, some dimensionless coupling times N2 plus K4 times N4, where K2 and K4 are related to the continuum gravitational coupling constant and cosmological constant in this way here. And you can exchange this. There are some thing called then Somerville relations between the number of subsimplices in a triangulation, which means that you can relate this to this thing here, where you exchange K2 with K naught. So we have usually done this, which is a mistake, I now realize, but that's too late because we have published many articles where you use K naught, but nevertheless, that's how it is. So the action is amazingly simple. And we kind of generalized this action. So you see that it's just linear in the number of these building blocks. And we then, in a Wilsonian spirit, we kind of generalized it to a slightly more general expression where we, so when you go back and you see these building blocks, there are two kinds of building blocks. You can say when we have this time foliation, namely this building block where we connect here, and this kind of building blocks. These are the two different ones, and if we can put in a different weight for these, we don't have really a precise kind of geometric interpretation of this, but in a Wilsonian sense, this is a natural generalization, and then it can be written like this. Instead of these two coupling constants, we keep the K4 here, but then we have a delta for some ratio between these. So we have three coupling constants, K0, delta, and K4 in our theory. And then we have our path integral. This is the continuum path integral. Now we replace it by our Lorentzian path integral where we sum over these Lorentzian triangulations. But for each of these guys, we can make a rotation to Euclidean space. And then we have what we call the Euclidean CDT path integral, which can now be written as a sum of all triangulations. There is some combinatorial weight here, which I will not discuss. Then there's the action, and the action is very simple. It only contains N2 and N4. So we can split the sum over all triangulations in a summation over N2 and N4, and then the number of these triangulations. So here's a remarkable fact that the partition function of quantum gravity is just the generating function of the number of abstract triangulations with a given number of N4 simplices and N2 simplices. So it is purely geometric, kind of combinatoric. And that is actually what allowed this whole industry of two-dimensional quantum gravity, Liouville theory, and so on, to take off and be solved exactly. This was because in 2D you could count this number here. Unfortunately, in 4D we cannot really count it, so we have to rely on computer simulations to count it for us. But that's basically kind of quantum gravity. You can say this must be much too simple. But my point of view is the opposite. It's wonderful that it's so simple, and it gives us a hope that one day we will understand kind of quantum gravity, four-dimensional quantum gravity, in a much more profound and simple way. But now we have to face the fact that it is a kind of the theory is not renormalizable. Well, it's easy to make it a renormalizable theory. We can just add an R-squared term. This was already done by Stelle in '77. This makes the theory asymptotically free. The problem was, as already have been discussed in other talks, the problem with unitarity. So another route was taken by the asymptotic safety scenario by Weinberg and also other people. And it has been implemented via the functional randomization group approach. Here one investigates whether one can find a non-perturbative ultraviolet fixed point in a Wilsonian formulated theory of quantum gravity. And so far, one should say that this functional randomization group has provided support for this idea, that such a scenario is satisfied. So four-dimensional CDT has a reflection positive transfer matrix. One can prove that. And in lattice theories, having such a reflection positive transfer matrix guarantees that if a continuum limit exists, then the corresponding theory is unitary. So probably whatever CDT is in the continuum limit, it would not have the problem of non-unitarity. So that's a good thing. And lattice field theories as such are well suited to investigate fixed points and the corresponding continuum limits. So thus it seems, on the surface at least, that CDT is ideally suited to address the asymptotic safety scenario. Let me spend a little bit of time, although I don't have it, on trying to recall how this is done in standard lattice gauge theory. So actually here I will repeat a little bit of what Kai Christoph already told us, but I guess it never harms to repeat the wisdom words of of Christoph. So I will. So he actually said a number of these things, but let me repeat it here in the context which is suited for our discussion. So the prime example of a lattice theory where you can take the continuum limit is the asymptotically free theory. Yang-Mills theory is the best example of that. So one just has one bare coupling constant. Let's call it G0. From perturbation theory, we know that there is an ultraviolet fixed point when G is equal to 0, and one can calculate the beta function either on the lattice by lattice perturbation theory or in the continuum. Anyway, it's given like this, where A is the lattice spacing. So this is the ultraviolet cutoff. And of course, to the first approximation here, one can just solve for A, and you see that when G goes to 0, A goes to 0. So this is how we can take the continuum limit. And in actual lattice simulations, when one puts things on and one wants to address some physics, like measuring the strain tension, the glue balls, or if you have a more complicated theory where we also include fermions, then the masses of pions and whatever, one just kind of measure this dimensionless mass, which one has to, of course, to define in the lattice context. This has to be equal to the physical mass times the cutoff, simply for dimensional reasons, that one has a relation like this. This exists when the cutoff is going to 0, and because of this relation, then we know exactly what we should measure if such a continuum mass exists. We should measure, as a function of G0, a behavior like this. And this is done. This is beautiful. It's done on the lattice, and you can see this. And of course, this formula is the famous dimensional transmutation, where the cutoff is exchanged for a non-perturbative scale, lambda Yang-Mills. So here, everything is clear. Now let us turn to a non-Gaussian fixed point. And as a nice example is the phi to the fourth theory. So here I've written down the Lagrangian for phi to the fourth theory. Of course, you can put this on the lattice, so let's imagine that we have done this. You can define a renormalized coupling constant in terms of this bare theory. I will not go into the details of this. There are many definitions, but anyway, there's a specific definition such that for any value of m0 and lambda, you can calculate this thing. So now we are on the lattice, and let's take the coupling constants, both this and this, to 0. Then we are here. This is just a free field theory. Both on the lattice, you can define it, and in the continuum, of course, this is free field theory. This operator is a relevant operator. When you move out here, you will get a mass added to your theory. And you can approach this point here by tuning the mass to 0 in such a way that in the continuum theory, you get a free massive theory, not a massless theory. But on the lattice, this has, and also in the continuum, there is a unbroken phase where the excitation value of phi is 0, and there's a broken phase when this m is negative. Along this line, the correlation length is infinite. So this is a second order phase transition if you view it as a statistical system, and the correlation length is infinite. And of course, the question one asked in the old days was that, here it was clear that we didn't get an interacting field theory when we took the continuum limit, but we would like to have an interacting field theory here. Anyway, this appears more or less in the standard model. So it wouldn't be nice to have an interacting field theory which exists at all scales. But this requires that there is an ultraviolet fixed point here. So how do we find this ultraviolet fixed point? Well, what is physically characterizing this ultraviolet fixed point? Well, this is the fact that this renormalized coupling constant should exist when we take the lattice spacing to 0. So now let's take an arbitrary point here in the m0 lambda space. Here, we can then use our definition to calculate this value. So it has a certain value. At this point, it would have a different value at a third value here. But then we follow the path where we change these bare coupling constants such that this renormalized one stays fixed. And then we are guided automatically to the ultraviolet fixed point. So here we will get also to the ultraviolet fixed point, and here also, depending on where we start and following this track, the kind of renormalized coupling constant will have a different value, but it will exist and be non-zero. So we would have an interacting theory here, and you can also scale the mass to a given value at some point. So this would exactly be an interacting phi to the fourth theory. So this is beautiful, except that what happens when if you would do the calculations, is that you start out at one point here, and then you follow this path of constant renormalized coupling constant, but you never reach this point here. So the conclusion was that there is no ultraviolet fixed point. So there's only this infrared fixed point. And if you, the correlation length along this line goes to infinity when we reach this point, and here it never goes to infinity. So we cannot, we can define a renormalized coupling constant, but we cannot take the lattice spacing to 0. So the ultraviolet limit doesn't exist, even if there's an effective theory with a kind of renormalized coupling constant. So that is the story. And here I've drawn the beta function if there has been an ultraviolet fixed point. So here it starts out with the infrared fixed point, and then it will cross here. So this was what kind of Christoph also explained to us. It will cross here at some fixed point with some slope, and at this slope you can just kind of linearize the theory, and then you put in to the normalization beta function group, and you can integrate it, and you find that the lattice spacing, it goes to 0 when the derivative of this function is negative. So this is negative, it means that it's an ultraviolet fixed point. And then we can define a continuum limit. So that is the story. So let's go to CDT. So what is the story there? Well, here's the phase diagram for CDT, determined by Monte Carlo simulations, so it's actually a complicated phase diagram. I mean, the red lines are second order transitions. So this is where some potential correlation length could be infinity. We haven't really defined a correlation length, and that's a kind of problem, an annoying problem, I would say, but that's how it is. But we would like to so I've drawn the phase diagram here, but only with two coupling constants. So the K4 multiplying this N4 is not really in our phase diagram, because we can only do the computer simulations with fixed N4. So this doesn't appear as an effective coupling constant. We can simulate with different N4s, but during the simulations, somehow our measurements are all done with fixed N4. So this is just technical reasons, but that's how it is. So this phase is not interesting, and this phase is not interesting from a continuum point of view, as I will show to you. But this phase, which we have called de Sitter phase, for reasons I will explain in a second, is very interesting. And then this phase here is not so interesting, but still interesting because it appears at the phase transition line here. And in particular, this phase transition line has a very simple interpretation. So here we imagine, and as far as we can judge, this is the case, that these spaces slices are homogeneous and isotropic. But when we cross this line, this homogeneity is broken. So it's a symmetry breaking transition, exactly as the phi to the fourth transition I told you. And then it would be very nice if there was an ultraviolet fixed point somewhere, maybe here. This almost screams to us that if there is an ultraviolet fixed point, it should be here. And I should also say that I mean, this phase, this means that there would be an ultraviolet short distance physics associated with this breaking of symmetry. And well, when you think about cosmology and short distance, then it could have, if it turned out to be true, implications for cosmology. That the nature of this phase transition is breaking symmetry, breaking homogeneity and isotropy. And that would then propagate all the time today with the formation of galaxies and so on. Of course, one should really define what it means to be homogeneous and isotropic in a quantum space-time. So Lowell and Silva has actually discussed this recently. I have no time to go into this. But let us take a short look at the structure of the geometries that we see in the computer. So I've dropped here the delta for clarity and just the bare coupling constant K0, which is formally proportional to 1 over G, the gravitation coupling constant. So when this bare coupling constant is small, there is no space-time. Time collapses to just a single slice here. And when it is very large, there's also no interesting space-time because all spatial slices are basically not correlated at all. They just fluctuate randomly. But in between, a blob is formed, and in the de Sitter space, this scales as a real four-dimensional. So if you have N4 as a measure of the total 4 volume, then the height of this scales as N4 to 3/4, and the width of this scales like N4 to 1/4. So it is really like a spatial blob. But you see that this figure illustrates exactly the point that I made in the beginning, that no background is put into this. I mean, so space-time can form and be anything, and for arbitrary bare coupling constants, it has nothing to do with our world, but there is a certain range of coupling constants where it might be connected to our real four-dimensional world. So this is really an emergent symmetry. So, oops, yeah. But that's a coffee break afterwards. So, yes, but I'll soon be done. So anyway, here I show such a computer-generated thing where this is the 3 volume at the spatial slices, which is plotted up here, and this is the time here. So here you see the blob, and this is a real configuration, and then you take the average of a couple of millions of these, and then you get this beautiful red curve, and here it is where also the error bars, the size of the error bars are measured, and you see that the expectation value it fits perfectly the cosine cube. If I were drawing a cosine cube curve here, you would not see the difference from the red curve. And this is exactly the spatial volume profile for some sphere, force sphere, if you use this metric here. So this is why we say that four-dimensional de Sitter-like space emerges. And the fluctuations, they scale like this. So the fluctuations, they scale like the square root of N4, while the, while the height here, it scales like N4 to the 3/4. So when we increase N4 for a fixed value of the coupling constant, then these fluctuations, they go away, and we get an infinite volume limit, but that's just an infinite volume limit. So we have obtained the goals declared in the beginning. We obtain an emergent geometry, and we can study fluctuations. And in fact, we can do much more. We can find an effective mini-superspace action and so on. I don't have time to talk about that. But now let me relate it to continuum physics and the ultraviolet fixed point, because that was the purpose of this. So unfortunately, we don't have access in an easy way to some correlation links here. And this has to do with how to define two-point functions and all kinds of things like that. It's a long story, a very interesting story. I will not tell it. But we have to do something else then. So we, as a correlation length, not as a correlation, but as a length scale, we simply take the size of the system, so the size of our universe. And as an observable, I put it in quotation mark, we take this dimensionless coupling constant lambda times g. Now, if I use the simplest functional randomization group truncation, in fact, the one first used by Martin Reuter when he calculated this, it is just the Einstein-Hilbert action, but with running coupling constant. And then if you take the classical solution to this and just do quadratic fluctuations around this, then you get that the fluctuations of V3 in the spatial slice divided by V3, it goes like the square root of this, and if you use these dimensionless coupling constants, it goes like this, where this K is the scale. This is the momentum cutoff. I know that functional randomization group people, they will not call it momentum cutoff, but still it's running to when it goes to infinity, this is the ultraviolet, and when it goes to 0, this is the infrared. So I will just call it momentum cutoff and identify it with our diffeomorphism invariant lattice cutoff in the following way. So here I just grabbed a figure from a recent article by Renata and Martin to show how this quantity behaves, how they imagine in the functional randomization group how it behaves. In the ultraviolet, it goes to the ultraviolet fixed point value, which is for order 1, And if you look at it, what it is today, it is quite small. So there is a huge growth there, and this is some approximate form which I described for this. There was a beautiful talk on Monday by Nobuyushi, where they actually calculated this this beta function, and it goes like this. So here is the ultraviolet fixed point, and you see this is like this 5 to the 4th theory ultraviolet fixed points which didn't exist, but here it seemingly exists. So, and then we find that the lattice spacing should go like this. Unfortunately, this is very small, so it's a huge factor here. So, but this is actually exactly what we measure. I mean, we are measuring this thing here, and we find an expression like this. And now, if this should stay constant, then n in 4 should go to infinity, then we would like, if there is an ultraviolet fixed point, then we would like this thing to stay constant. So the lattice spacing go to 0. It means that this coefficient that we measure in the fluctuations, it should go to infinity. But that's kind of natural that something like that should happen at a fixed point or at a phase transition, that the fluctuations should grow to infinity. So it is not, from this point of view, unlikely. So let us assume that we can find a fixed point where it diverges like this. Then this thing is constant if we can find, if we choose a path of n4 going to infinity, which compensates for this. So this can be checked directly by Monte Carlo simulations. So this is a thing we can do. Unfortunately, the results are a little bit inclusive because it requires very large volume. But in the case of an ultraviolet fixed point, then we would say the A scales to 0 like this, and this should be exactly the coefficient which is calculated in the normalization group approach. So here I've drawn the phase diagram again, and what we should see, what we can do is that we can follow a path like this towards this tentative ultraviolet fixed point where this is staying constant. So this is what the normalization group expect, that close to the ultraviolet fixed point, this should stay constant. So we follow this path, and this should lead us to this fixed point. So this is my last slide. So at the Monte Carlo simulations, we see that this indeed increases when we go this direction, at least by a factor 10. And moreover, whenever we can increase n4, it's not so easy, then we have been able to obtain more convincing signs that this is an ultraviolet fixed point. But it's not settled yet, I would say. Definitely not. But if it is, then we have a continuum limit where we can remove the cutoff. So just to give you, I'm done basically, but just to give you an idea of what we are talking about, because we are saying we are doing lattice simulations and so on, what kind of universes, what is the size of universe we are talking about? So the best we can do here is around 500,000 of n4s in the computer. I now put these guys in a hypercubic lattice, pack them in some way in a hypercubic lattice. How large is this hypercubic lattice? It is 10 to the 4th. So it's a small lattice. I mean, this is our universe. It's 10 to the 4th. So there is a limit to what we can expect to study in such a universe, which is just a lattice of 10 to the 4th, lattice spacings. And that's why I'm saying there are huge finite size effects still. What can maybe be a hope that what we see is good is that if you think about lattice computer simulations of Yang-Mills theory, the best result ever obtained in these simulations were the very first one by Michael Kreutz in 80 on a 4 by 4 by 4 by 4 lattice. Since then, the results has only got worse. Of course, I mean, today we laugh at his results, but nevertheless, he got everything right in a certain way. So maybe even if our lattice is not larger than 10 by 10 by 10 by 10, still maybe it tells us some truths. But it is also clear that there's a limit to what we can study. I mean, there cannot be many black holes and so on embedded in such a lattice. I mean, so one cannot hope of studying this thing. But maybe one can hope of answering the question whether there is an ultraviolet fixed point. And that in itself, I think, would be quite interesting. Thank you very much for your patience.
Thank you very much, Jan. Let's have a quick question before we go for coffee. Here, wait.
Just because the session was about the causal structure, I like to hear a little bit of this story of how this started with being dynamical triangulations and it didn't have a causal structure embedded in, and then you didn't get this continuum limit, and suddenly, I mean, you changed radically your configurations, and then everything worked. If you can elaborate a little bit on that story.
Yeah, I can. Well, I can elaborate on it in the following sense that, strictly speaking, we have, of course, no idea what we get. So there are several steps here. I mean, so each triangulation starts out with a Lorentzian geometry, which is, of course, causal by construction. So that's fine. But then, as also kind of Christian remarked, then we sum over all possible triangulations which have different causal structures. So what the outcome of this is not so clear. But what we then do in addition, of course, which makes everything much more murky, is that we rotate to Euclidean space. So each of these configurations can be rotated to Euclidean space, so we can rotate back and forth there. But now we sum over all of these guys. As long as the sum is finite, we can rotate back. But but of course, in the infinite limit, rotation back and forth is a subtle thing. From a numerical point of view, it's not so easy to rotate back and forth. In fact, it's almost impossible. Terms which can be subleading in the Lorentzian can be important in the Euclidean. But this is known from ordinary quantum field theory also. I mean, there are something you can measure in the Euclidean lattice field theories in a good way, and something is almost impossible to extract unless you have some ingenious ideas like scattering amplitudes and so on. They do not come easy to you. But the Green functions, you can measure there, and then you can say, okay, I know how to rotate my Euclidean Green function back to Minkowski space in flat space. This is the Osterwald-Schrader axioms that the Green functions, they are rotated back exactly in the right way. But here in gravity, of course, I'm afraid we don't know. Yeah.
Okay, so there is another question by Daniele, perhaps. And that will be the last question.
So thanks, Jan, for the talk. I haven't understood how you characterize the transition as a breaking of homogeneity and isotropy. Which observable do you use to characterize that?
Yeah, okay, thanks. Yeah. Well, that's very easy and naive, but probably correct. So on the other side of the phase transition, what is happening is that the geometry becomes kind of degenerated. So a single vertex gets an order which, if you move inside this, is of the order of N4. I mean, so the whole universe is centered around a single vertex or a single link of very high order. So clearly such a situation, I mean, you don't have any homogeneity because everything is kind of linked to this vertex. That is what we say, just looking at it, extremely naively. While in the other phase, of course, you have distributions of order of vertices, but they're all continuous distributions, and we have seen nothing special happening. But of course, one has to quantify this. What do you mean by things being homogeneous and isotropic? Of course, any individual triangulation is not homogeneous and isotropic, but just some arbitrary kind of triangulation. So some property of the average which we take should be satisfied. And this is exactly what Renate studied in the recent article. But you should ask her about how to define it better than just looking at this and say, oh, it looks pretty homogeneous. so that's how it is. Yeah. Yes.
Okay, thanks. So we'll have coffee now and start again at 11. Let's give Jan another round of applause.